And there we were working out on what later on I would describe as ingredients, and we worked out together 4 ingredients in this methodology. And soon after that, it was about putting together the ingredients. And something interesting there was basically whenever Helmut was going into demand estimation, getting close to demand to collapse, those demands would be very challenging. So we started breaking that into a process. Some of you may remember this slide in terms of what you get if you mix the blue and the yellow, you get the green, and what you get in the blue, the yellow and the red, you would get the orange. And of course the orange was very important because it's the part that Helmut was working on, collapse. And the orange was important because that's Helmut's color of his car. We then move on, basically extending the concept of loss disaggregation, in which seismologists would be interested in knowing what basically contributes to the hazard at your site, what is the magnitude and the distances and the epsilons contributing to the hazard. And we basically did the same thing for losses. And we were trying to provide power to the structural engineers into knowing where the losses, what's the portion that is coming from collapse and non-collapses, or perhaps disaggregating into structural and non-structural components. He remained being a structural engineer, and he sort of gave me the charge of becoming a non-structural engineer, which I've enjoyed very much over the years. Then with Hassan, we worked on a tough problem, which is, we're not able to get all of what we wanted to model into open seas. And I was getting very frustrated because, at least my side of the engine was not working, making all sorts of strange noises, smoke coming out of it, and it was really going back to the blackboard and apply the Krawinkler approach and try to get some sort of a piece that would work and take care of the problem. And that's what we did with this loss vertical carrying capacity. And then it came more recently, and his side of the engine was working perfectly. I mean, it was fine, running fast. I'm always sort of in this eternal catching up mode. And his side of the engine was going so fast and mine so slow that I thought we were starting to go in circles, lots of torsion. So again, I needed to go back and apply the Krawinkler approach. Just basically sitting on that car and just observing his approach and trying to replicate that. And this is one example of what he's been doing, how great his side of the car was working, looking into collapse and estimation of collapse capacities. And Helmut, I know that you love the orange, but I wanted to make a point here, so get rid of your nice orange for a second. And basically, you probably noticed a lot of smoke coming out of Bloom Center lately. And it's not the kind of smoke coming out of your office when you were the director. It's some other kind of smoke coming from the oven. And there's been a lot of hardworking students basically working on the kitchen and for a special cake that we wanted to present in this occasion. And I must say that this cake comes with a little warning label, but I know that you've ignored this kind of warnings for a lot of years, so as a matter of fact, we're counting on you to ignore this warning label and try this cake. Because basically what we've been trying is to change the recipe, pretty much. And we thought that 2 ingredients was not good enough. It's sort of like an apple strudel with just pastry and apples, and thought that there was something missing. So this just non-collapse losses and collapse was not enough, so we went ahead and added a 3rd ingredient. And that 3rd ingredient is, of course, something that we have ignored and bothered me for a long time, but that is basically the possibility of having to demolish your structure even though you haven't collapsed it. And so he had his color in this ingredient, so I had to add my own. And if you're wondering what that strange pink is, it's a very famous color in Mexico. You find it all over the place. place in the Bougainvilleas, and then famous painters like Tamayo or architects like Barragan or Legorreta made it famous. And let me tell you a little bit about what that third ingredient is. But the idea is relatively simple. It's how much you may lose or how much it's going to take you to replace that structure if you have to demolish, times the probability of having to demolish it. So really, what goes complicated is trying to get this probability of this event happening. And that basically meant, what is the probability of having to demolish your building? And then, of course, times good old Helmut's ingredient, 1 minus the probability of collapse. That's your probability of non-collapse. So we thought, well, you know, what do you do? Or what drives you into having to demolish a structure? And it's very clear in structures like these that you will have to demolish them. But what is interesting is that there's these other structures that have much smaller residual displacements, and they basically go on the same path. Going back to 85, you know, I would say that there were not that many buildings that had to be demolished in Mexico City after the earthquake. In Mexico City, of course, labor is inexpensive, so you can repair lots of things. And for example, this column, Helmut, you may remember it, but this is a building that's been damaged pretty badly in 2 earthquakes. You may notice the strange reinforcement from a jacketing from a previous earthquake in '79 got repaired, got damaged again. And if you go to Mexico City today, it's still there. But then there were these other buildings. Again, what some people would say, well, you know, this ductile concrete, you know, built in the late 50s. Well, this late 50s building had beautiful reinforcement. Probably in our methodology, we would say relatively little damage. If we were to apply today's peer methodology, we would miss big time what happened to the structure. Probably we would say, yeah, you know, damage about how many stories? 9 stories. Well, you know, maybe you lost 1/10 of the value of the building. Well, guess what? It had to be demolished. And probably I would say that other than Piazza del Miracolo, Pisa, we tolerate in Mexico City more inclined structures probably than anywhere in the world. And lots of structures are leaning, especially anything that's more than 200 years old. It's not straight. Yet, many structures, even with relatively small residual displacement, have to be demolished. So that's basically what we're doing in this ingredient, and we're trying to provide an estimate of this probability of demolition based on peak residual displacements. And these are 2, if you will, sub-ingredients that we're looking into. One is the probability of demolishing condition on the peak residual interstory drift of your structure. And that's what you see down here on the left, if you will. I mean, of course, if Alan was here, he would tell us to just fit a log normal probability distribution to that. But Helmut and I were not into the probabilities. We're more into touching ground and looking physically. So the way I interpret this is basically what's the proportion of buildings that would have that level of drift in which the structural engineer or the owner would decide to demolish it. So as you can see here, at about 1% residual interstory drift, we're saying, well, about 10% probability that it will have to be demolished. By the time you're at 2% interstory drift, that goes up very rapidly to about 80% chance of demolishing it. By the time you're at 3%, it's probably for sure that you will have to demolish it. And then, of course, you know, what is the probability that you will see that level of residual interstory drift as good old open seas engine